On the morning of August 7, 1945, Dr. Yoshio Nishina stood at the entrance of Tokyo's Riken Institute, staring at a telegram that had arrived just minutes earlier. The message was brief, almost impossibly brief for what it described. Hiroshima destroyed by single bomb of unknown type. The physicist had spent the last 3 years working on Japan's own atomic research program, and he knew immediately what those words meant, even as his mind refused to accept them. He believed, as did most of the world's leading scientists at the time, that a functional atomic weapon was still years away from reality, perhaps even a decade. He would be proven catastrophically wrong within 72 hours. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you are watching from. It really helps support the channel. What Dr. Nishina and his team would discover in the ruins of Hiroshima would not only confirm humanity's entry into the atomic age, but reveal a geological transformation so profound that it would create an entirely new material, one that would become a permanent marker in Earth's stratigraphic record and force scientists to confront what humans had become capable of achieving. The telegram sat on Nishina's desk for nearly an hour before he moved. Around him, junior researchers continued their work, calibrating instruments, recording measurements, unaware that the project they had devoted years to had just been rendered obsolete by an enemy they had underestimated. Dr. Nishina was 54 years old, a graduate of Tokyo Imperial University who had studied under Niels Bohr in Copenhagen during the 1920s. He had published papers on quantum mechanics, contributed to the theoretical understanding of particle physics, and spent countless hours trying to convince military officials that Japan's atomic program needed more resources, more time, more uranium. Now, staring at those 11 words on paper, he understood that time had run out in the most spectacular way possible. He picked up the telephone and placed 3 calls. The first was to the Army headquarters, requesting immediate authorization to travel to Hiroshima. The second was to Dr. Tsunesaburo Asada, a geologist at Tokyo University who specialized in mineralogy and high-temperature materials. The third was to his lead assistant, instructing him to prepare field equipment for sample collection under extreme conditions. None of the men he spoke with asked why. They all understood what a single bomb capable of destroying an entire city meant, even if they could not yet grasp the full implications. The authorization came through within 2 hours, marked urgent by officials who were still trying to understand their own intelligence reports. A city of over 300,000 people had simply ceased to exist between 8:14 and 8:16 on the morning of August 6th. The reports coming from survivors were contradictory, impossible, describing a flash brighter than the sun itself, a wave of heat that turned people to shadows on stone walls, a wind that flattened buildings made of steel and concrete as though they were paper houses. Military commanders wanted answers. They wanted to know if more of these weapons existed, if other cities were at risk, if there was any defense against such a thing. Nishina could not give them those answers, not yet, but he knew where to start looking. The train journey to Hiroshima took 16 hours, traveling through the night on tracks that had been damaged by conventional raids and hastily repaired. Nishina sat in a military car with Dr. Asada and 2 army officers who said nothing for the entire trip. Through the window, he watched the countryside pass in darkness. Small villages with paper lanterns glowing in windows, farmers working late in rice paddies. A world that did not yet understand it had changed forever. Asada spent most of the journey reading a technical manual on glass formation, making notes in margins with a pencil that he sharpened repeatedly with a small knife. They arrived at a temporary military station 15 kilometers outside Hiroshima just after dawn on August 8th. The officer who met them, a major whose uniform was covered in grey dust, took one look at the scientists and said they should prepare themselves for what they were about to see. Nishina asked if the fires were still burning. The major nodded and said some of them would burn for days, maybe weeks. There was nothing left to put them out with. The city's water system had been vaporized along with everything else. The approach was made on foot, following a road that had once been lined with shops and houses, but was now just a corridor of ash and twisted metal. The temperature was already climbing toward 35 degrees, and the smell hit them first, a combination of burning wood, melted rubber, and something else that none of them wanted to identify. They wore cloth masks that did nothing to filter the air, only made breathing harder. After 2 kilometers, they began to see the bodies, or what remained of them. Nishina had been in Tokyo during the firebombing raids, had seen destruction on a massive scale. But this was different. This was not destruction, this was erasure, the hypocenter. The point directly beneath where the bomb had detonated was marked by the ruins of what had once been a hospital. The building's concrete frame still stood, partially, twisted into shapes that seemed to defy physics. Everything flammable within a kilometer radius had been completely incinerated, leaving only stone and steel, and even those materials had been transformed. Nishina walked slowly through what had been streets, careful not to step on the pieces of tile and brick that littered the ground, each one a potential sample, a piece of evidence. He kept his eyes on the ground because looking up, at where buildings should have been, at where the sky was too visible, was too overwhelming. It was Dr. Asada who first noticed the glass. They were standing near the remains of a shrine. Its stone steps melted into a flowing form that looked almost liquid, despite being solid. Embedded in the surface were hundreds of small green beads, irregularly shaped, unlike any natural glass formation either scientist had seen. Asada knelt down, pulled out a collection kit and carefully extracted several samples using metal tweezers. The beads were still slightly warm to the touch, even though more than 48 hours had passed since the detonation. He held one up to the light, turning it slowly, and Nishina saw immediately that the material was not uniform. It contained layers, bubbles, particles of other materials trapped inside. Then Asada said what they were both thinking. This is melted sand. And something else. They spent the next 6 hours collecting samples systematically, working outward from the hypocenter in concentric circles, documenting the exact location of each find. The glass beads were everywhere once they knew what to look for, scattered across the ground like strange rain. But the most dramatic formations were found where the heat had been most intense, within 300 meters of the detonation point. Here, entire sections of ground had melted and re-solidified, creating surfaces that looked like glazed pottery. Stone walls had flowed like candles. Metal poles had been bent into curves that should have required hydraulic presses to achieve. And everywhere that strange green glass, cooling into shapes that nature had never intended. By early afternoon, they had collected more than 50 samples, each carefully labeled and stored in wooden boxes lined with cotton. Nishina photographed each location, measuring distances with a surveyor's tape, recording angles and orientations. The army officers who accompanied them kept their distance, uncomfortable with the scientific precision being applied to what was, for them, simply a scene of overwhelming tragedy. One of them asked how long the area would remain dangerous. Nishina could not answer. Nobody knew. Nobody had ever studied the aftermath of an atomic detonation before. They left Hiroshima just before sunset, carrying their boxes of samples and several notebooks filled with observations. On the train back to Tokyo, Asada examined the glass beads under a portable magnifying lens, making sketches of their internal structures. He pointed out to Nishina that the bubbles trapped inside were not random, but seemed to follow patterns, as though the material had been cooling while being subjected to intense pressure waves. The green color came from iron and other metals in the soil, he theorized, oxidized during the intense heat and incorporated into the glass matrix as it formed. But the temperatures required to melt sand into glass were enormous, typically over 1600 degrees Celsius. And these formations had occurred not in a furnace over hours, but in a fraction of a second, across an area of several square kilometers. The implications were staggering. Nishina did mental calculations based on the energy required to achieve such widespread melting, comparing it to the theoretical yields his own research team had projected for atomic weapons. The numbers did not make sense. They were too high. If the glass formations extended as far as they had observed, if the melting had occurred as rapidly as the evidence suggested, then the bomb that destroyed Hiroshima had released energy equivalent to somewhere between 12,000 and 15,000 tons of conventional explosives. It was a scale of destructive power that made conventional warfare obsolete. The laboratory analysis began the next morning in a basement facility at the Riken Institute. Nishina had assembled a team of 6 specialists, Each assigned a specific aspect of the investigation. Dr. Asada led the geological analysis, examining the mineral composition and formation temperatures of the glass samples. Dr. Kenji Nakamura, a chemist, analyzed the samples for radioactive isotopes using a Geiger counter that had been built for the Japanese atomic program. Dr. Hiroshi Tamaki, a metallurgist, studied the deformed metal samples, looking for clues about the pressures and temperatures involved. And Nishina himself coordinated the effort, compiling data, making calculations, trying to reverse engineer a weapon he had never seen from the evidence it had left behind. The first results came back within days, and they were more disturbing than anyone had anticipated. The Geiger counter clicked steadily when held near the glass samples, indicating measurable radioactivity. This was not unexpected, as nuclear fission produces radioactive byproducts, but the pattern of isotopes was unusual. There were traces of uranium-235, the fissile material, but also significant amounts of neptunium, plutonium, and dozens of other elements that could only be produced in a nuclear reaction. More telling were the fusion products, elements that should not exist in nature, created when atoms were literally torn apart and reassembled into new configurations. Each sample told the same story: temperatures in excess of 6,000 degrees Celsius at ground level, pressures of several 100,000 pounds per square inch, and radiation levels that would have been instantly lethal to any living thing within a kilometer radius. Dr. Asada's analysis of the glass structure revealed something equally remarkable. Under microscopic examination, the samples showed clear evidence of having been melted, vaporized, and re-solidified in layers, sometimes multiple times in the same piece. The internal structure suggested that the material had been subjected to multiple shock waves, each one powerful enough to liquefy stone. The first wave, the initial blast, had created the primary melting, but subsequent pressure waves reflecting off the ground and buildings had reheated the material several times before it finally cooled. This explained the layered structure, the trapped bubbles, the unusual formations. The glass had not formed once but had been repeatedly transformed during the first few seconds after detonation. What they were looking at, Asada explained to the team during a briefing on August 12th, was a new category of material. It was not volcanic glass, which forms from lava cooling over hours or days. It was not fulgurite, which forms when lightning strikes sand, creating narrow tubes of glass. This was something different, a substance created by technology rather than nature, a permanent marker of human capability. He suggested they needed a name for it, something that would distinguish it from natural glasses in the geological record. Nishina proposed combining the Greek word for atom with the word for glass, creating the term trinitite, after the Trinity test site where the Americans had detonated their first atomic device weeks earlier. But it was another discovery that truly shocked the team. Dr. Nakamura, while analyzing the radioactive isotopes in the samples, noticed something unexpected in his measurements. Some of the samples contained traces of plutonium, a synthetic element that does not exist in nature and can only be produced in nuclear reactors. This was significant because Japan's atomic program had focused on uranium enrichment, and the scientists knew that plutonium-based weapons required a different, more sophisticated design. The presence of plutonium meant the Americans had not only built a functional atomic weapon, but had done so using multiple designs, multiple fuel sources. They had industrial-scale production capabilities. They had options. Nishina sat alone in his office that night, reading through the compiled reports, understanding with perfect clarity what they meant. Japan had been racing to build a single experimental device, struggling with uranium enrichment, debating theoretical designs. The Americans had already deployed at least one, possibly two different types of atomic weapons operationally. The industrial capacity required to produce refined uranium or plutonium in weapons-grade quantities was enormous, requiring entire facilities dedicated to the task, consuming vast amounts of electricity, employing thousands of workers. And they had done all of this in secret, while simultaneously fighting a global conflict on multiple fronts. It was not just a technological victory. It was a demonstration of industrial supremacy so complete that any thought of continued resistance became absurd. The second bomb fell on Nagasaki on August 9th, while the team was still analyzing samples from Hiroshima. The news arrived via radio, and Nishina immediately understood what it meant. The Americans were not bluffing. They had multiple weapons. They were willing to use them on civilian populations, and unless Japan surrendered immediately, more cities would be targeted, perhaps Tokyo itself, perhaps the facility where he now stood. The research team continued working, but the urgency had changed. They were no longer investigating an isolated incident, but documenting a new era of warfare, one where a single bomber could accomplish what previously required fleets of aircraft and months of conventional bombing. The formal report was completed on August 14th, just hours before Emperor Hirohito announced Japan's surrender. It was a technical document, filled with measurements, photographs, chemical analyses, temperature calculations. But buried within the data was a simple conclusion that Nishina wrote himself. The weapon that destroyed Hiroshima represents a fundamental shift in the nature of conflict. No defense currently exists against such devices. No city can be protected. No conventional military force can counteract the strategic advantage they provide. Continued resistance in the face of such overwhelming technological superiority serves no rational purpose. The report was delivered to military headquarters that evening, though whether anyone read it before the surrender announcement is unclear. What is certain is that Nishina's team had provided the scientific confirmation of what Japan's leadership already suspected, that the conflict was over, decided not by courage or strategy or willpower, but by industrial capacity and scientific knowledge. The Americans had built something that changed the fundamental equations of warfare, and they had done it first. In the months following the surrender, as occupation forces arrived and the complex process of rebuilding began, Nishina's research took on new significance. American scientists, arriving to study the bomb damage themselves, were surprised to find such detailed documentation already existed. Teams from Los Alamos and the Manhattan Project reviewed Nishina's findings, confirming his calculations. Impressed by the precision of the analysis despite the limited resources available, the glass samples were shared, studied, compared to similar formations found at the Trinity test site in New Mexico, and slowly a new field of study emerged, one focused on understanding the geological and environmental impacts of atomic weapons. Dr. Thasada continued his research on the glass formations for the next 3 decades, becoming one of the world's leading experts on impact glasses and high-temperature materials. He published dozens of papers on the Hiroshima samples, each one revealing new details about the formation process, the mineral compositions, the physical properties. The green glass beads, initially seen as simply curious artifacts, became recognized as important markers in the geological record, evidence of the Anthropocene, the age when human activity began to leave permanent marks on the Earth itself. Museum collections around the world acquired samples, each piece carefully labeled with its collection location and date, preserved as evidence of a moment when everything changed. The term trinitite never became standard, as researchers eventually adopted location-specific names for the glass formed at different atomic test sites. The Hiroshima material became known as Hiroshima-ite in geological literature, distinguished from Nagasaki-ite, and the various forms of trinitite produced at American, Soviet, British, French, and Chinese test sites in the decades that followed. But the underlying reality remained the same. Humans had learned to create materials that nature had never produced, substances that would persist in the geological record for millions of years, markers of technological capability and destructive power that future civilizations, if any emerged, would be able to identify and date with precision. Nishina himself never spoke publicly about his work in Hiroshima, declining interview requests, avoiding conferences where the topic was discussed. He returned to theoretical physics, publishing papers on cosmic rays and particle interactions, training a new generation of Japanese scientists in a rebuilt Japan that had renounced warfare entirely. But those who worked with him noted that he kept one of the glass samples on his desk, a small green bead about the size of a pea, polished smooth on one side. When asked about it, he would say only that it was a reminder, nothing more. a reminder of what humans could achieve when they dedicated themselves fully to a task, for better or worse. A reminder that knowledge, once gained, could never be forgotten, and that some discoveries changed everything that came after. The full extent of Nishina's contribution became clear only after his death in 1951. Papers found in his personal effects revealed that he had immediately understood, even before completing the Hiroshima analysis, that the atomic age would require new thinking about international cooperation, scientific ethics, and the relationship between technological progress and human survival. He had written extensively about the need for global agreements limiting atomic weapons development, for international oversight of nuclear materials, for scientific communities to take responsibility for the implications of their discoveries. Many of these ideas would later be incorporated into the nuclear non-proliferation efforts of the United Nations, though Nishina himself never lived to see their implementation. The glass samples he collected remain in various institutions today, carefully preserved under controlled conditions. New analysis techniques, unavailable in 1945, continue to reveal additional details about the formation process, the isotopic compositions, the mineral structures. Each new study confirms what Nishina and his team documented in those first chaotic days after the detonation, that the Hiroshima bomb had released energy on a scale previously unimaginable, creating temperatures and pressures that transformed ordinary materials into substances never before seen on Earth, and leaving permanent evidence of humanity's entry into an age where the power to reshape matter at the atomic level had become reality. Modern geological surveys have identified additional sites where similar materials formed during the various atomic tests conducted between 1945 and 1996, when the Comprehensive Nuclear Test Ban Treaty was signed. Each site has its distinctive signature, its unique mineral composition based on local geology and bomb design. The Nevada test site produced greenish glasses rich in feldspar. The Semipalatinsk site in Kazakhstan created yellowish formations with high aluminum content. The Mururoa Atoll tests in the Pacific generated glasses incorporating coral calcium, and all of them, without exception, contain the distinctive isotopic signatures that mark them as products of nuclear reactions, materials that could not exist without human intervention. What makes Hiroshima unique is not its composition, but its context. It was the first such material created in anger rather than testing, formed over a living city rather than an empty desert, collected while the fires still burned and the injured still suffered. The samples carry that history within them, frozen into their atomic structure. Every analysis performed on them, every photograph taken, every measurement recorded, exists against the backdrop of what they represent. Not scientific curiosity but human tragedy, not achievement but loss, not progress but warning. The scientific community has developed protocols for handling these materials, recognizing their dual nature as both research specimens and memorial objects. Institutions that house collections of atomic glass maintain special repositories, climate-controlled rooms where temperature and humidity are carefully regulated to prevent degradation. Access is restricted, typically requiring specific research justifications and ethical review. And increasingly, these collections serve educational purposes, with small samples displayed in museums, alongside photographs of the cities before and after, testimonials from survivors, documents detailing the development of atomic weapons. The glass becomes a teaching tool, a tangible connection to events that might otherwise seem impossibly distant or abstract. Dr. Asada's final paper on Hiroshima, published in 1978, included a philosophical reflection unusual for a geological journal. He wrote that the glass formations represented more than just interesting mineralogy. They were evidence of a threshold crossed, a line beyond which the rules changed. Before Hiroshima, humanity's destructive capabilities were limited by logistics, by the need to deliver explosives physically to targets, by the constraints of conventional chemistry. After Hiroshima, those limits disappeared. A single weapon could erase a city. A coordinated strike could end civilization. The glass, he argued, should be preserved not as trophy or curiosity, but as warning. a reminder that some knowledge carries permanent responsibility, and that the capabilities we develop shape the world available to those who come after us. The irony that this understanding came from analyzing melted sand was not lost on contemporary observers. Sand, one of Earth's most common materials, transformed by extreme conditions into something new and permanent. It was an apt metaphor for what had occurred. Common elements, rearranged by unprecedented forces, becoming something that would outlast cities and civilizations. Future geologists, studying sediment layers a million years from now, would find a distinct marker corresponding to the mid-20th century, a thin layer enriched with radioactive isotopes and unusual gases, evidence that something extraordinary had occurred during this brief period of Earth's history. They would be able to identify the moment, even without historical records, when a species gained the ability to reshape matter at the atomic level and chose to demonstrate that capability on itself. The samples that Nishina collected in those desperate days after the surrender have been studied by hundreds of researchers across multiple disciplines. Physicists analyze them to understand blast dynamics and energy distribution. Chemists examine their isotopic compositions to identify bomb design characteristics. Materials scientists study their formation mechanisms to better understand high-temperature processes. Medical researchers investigate their radioactive properties to assess long-term health impacts on survivors. Environmental scientists use them as calibration standards for detecting other sources of radioactive contamination. Each new analysis adds another layer of understanding, another piece of the story, but the fundamental truth remains unchanged. The glass exists because humans built a device that recreated, for a brief moment, conditions normally found only in stellar cores, and deployed that device over a populated city on a summer morning in 1945. The children who now visit museums and see these small green beads behind protective glass often ask the same questions that researchers asked 80 years ago. What made the glass form? Why is it green? Is it dangerous? The answers have become standardized, repeated by docents and displayed on informational placards. The glass formed when temperatures exceeded 1600 degrees Celsius, hot enough to melt sand. It is green because of iron and other metals in the soil. It is slightly radioactive but safe to be near behind protective barriers. These simple explanations capture the basic science, but miss the deeper truth that Nishina and his team confronted during their analysis, that the glass exists as proof of what humans had become capable of, for better or worse, and that this capability could never be unmade, only managed or misused. The legacy of those 72 hours, from the moment Nishina received the telegram to the completion of his final report, extends far beyond the immediate documentation of bomb effects. His work established protocols for studying atomic test sites, methods that were adopted by American, Soviet, and later British, French, Chinese, Indian, Pakistani, and North Korean researchers as they conducted their own weapons programs. The techniques he developed for collecting and analyzing samples under hazardous conditions became standard procedure at test sites worldwide, and his recognition that the glass formations represented a new category of material, neither natural nor conventional industrial, helped establish the field of anthropogenic geology, the study of materials created by human activity that will persist in Earth's geological record. Perhaps most significantly, Nishina's immediate recognition of what the atomic bomb meant for Japan's military position influenced the surrender decision at a critical moment. While historians debate the relative importance of various factors in ending the conflict, including the Soviet declaration on August 8th and the internal political dynamics within Japanese leadership, there is no question that scientific confirmation of the bomb's nature and implications provided crucial data for decision-makers. When Nishina reported that the Americans possessed multiple atomic weapons, could produce more, and that no defense existed against them, he removed any technical basis for arguments that continued resistance might achieve better terms, or that the Hiroshima destruction had been an isolated event. The glass samples, analyzed with precision and documented with care, became evidence in the case for surrender, physical proof that the conflict had entered a phase where conventional military considerations no longer applied. In the decades since, as more nations developed atomic capabilities and the stockpiles grew to contain tens of thousands of weapons, with yields hundreds of times larger than the Hiroshima bomb. The glass samples have taken on additional meaning. They represent not just the first use of atomic weapons, but the boundary between two eras, the last moment when such devices existed only theoretically, and the first moment when their use became historical fact. Every atomic weapon built since, every test conducted, every treaty negotiated, every protest organized, every strategic calculation made, exists in the shadow of what those samples represent. The glass is evidence that humans crossed a threshold, gained a capability that previous generations could only imagine, and immediately deployed it in the most destructive way possible. The question that haunted Nishina, evident in his private writings and the recollections of colleagues, was whether this pattern was inevitable. Did the acquisition of atomic knowledge necessarily lead to atomic weapons? Did the existence of atomic weapons necessarily lead to their use? Could the technology have been developed differently, controlled more carefully, deployed only as deterrent rather than as weapon? These questions had no clear answers in 1945, and they remain unresolved today. But the glass samples stand as evidence that for humanity's first encounter with atomic technology, the path from discovery to deployment to use took less than 4 years, and the devastation was comprehensive and immediate. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II, and check out the video on screen for another incredible tale from history. Until next time.